Can you see my screen?
Yeah, it looks good.
Okay, good. First of all, thanks to the organizers for giving me the opportunity to present my work here. And thanks to everybody speaking before me for all the great talks. It has been a nice 3 days for me. And I think the science coming out of GALA and other spectroscopic surveys is great. And I think for us, or like I'm coming more from the simulator community, and I think for us as theorists, there's a pressing need right now to keep up with the amount and quality of the data we're getting in. And so basically what I'm presenting here is a step towards that, making cosmological simulations ready to keep up with all the spectroscopic data. And thanks to Chiaki, I now have a solid foundation with all the theory of chemical enrichment, so I can directly jump in and give you a head start. So I guess it is clear that with GALA, we now have the great opportunity to study various different elements in detail. And we see a lot of structure in here. There's like different trends in all the data. So some of the elements actually look quite similar and others look completely different. And I think Chiaki already told us where this is coming from, that we need to take into account the enrichment history and the different sources of the elements. Why is that? So yeah, the short motivation is we have now 30 abundances measured quite precisely, and combining, for example, GALA with Gaia data gives us precise kinematics, so we can study the chemo-dynamics of the Milky Way in detail. But the question for me is then, what we see here, the chemo-dynamical patterns of the Milky Way's stars, what do they tell us about Milky Way's formation history? And the problem with observations, like from my perspective, is we only get a snapshot of the present day. We only know the configuration of the present day, but we don't know how we arrived here. And we already saw that analytic models for the formation of these patterns are pretty good in reproducing the data. And this is taken from Sanjeev's work, and we have heard a lot about this in his talk. But let me remind you, the bimodality we see in alpha elements in the Milky Way disk can, for example, be described by these different tracks of birth radii, which then get mixed by radial migration. So basically, if we look at a solar neighborhood, what we see down here is a mixture of various different birth radii. And this is great that this model can explain this. And for me, it's also quite fascinating that it can do it, because it's based on, say, some simplified assumptions. And so we already saw a movie about the Milky Way, but let me start it again. We have here 3 different panels: the disk on the right, or the stars on the right, with a close-in view and a further out view. The gas temperature in the middle, and dark matter on the left. And this is now showing the evolution of a Milky Way in a cosmological context. And similar to the movie Chiaki showed, you can see that the disk is forming in the center, but there's lots of satellites moving around, getting disrupted, merging with the disk, puffing it up. There's stellar streams emerging at some point. And this is now redshift 1, roughly, half the age of the universe, and the disk is well in place, but still there's a lot of perturbers coming around. You can see here the nice disk where star formation is going on, all these little supernovae explosions, gas is cooling out of the enriched gas, forming then the next generation of stars. And I think this is not captured in all these analytic models. And for me, the question is, how important are these effects? What do they do to the disk? And as we have heard in previous talks already, can we pick up these features of tidal streams and merging galaxies from the data we see? And so in order to do this, oh yeah, sorry. In order to do this, I run cosmological simulations, and I think they right now are so sophisticated that we actually can reproduce key features of the observations. And just to show how well the analytic model and the prediction from the simulation here on the right, how well they fit, I put them next to each other. And so if we look on the right, the color coding is color coding of age. And so Sanjib's work, for example, says up here stars should be 13 giga years old, 12, 11, 10, 8, and then ever younger. And so this sequence basically in the simulation comes out as predicted in Sanjib's model. And on the other hand, the lower sequence here is basically of a unique age, similarly as Sanjib's work predicts. And now if we look at the birth radii of these stars, so I can go back and check in the simulation where have the stars been born. So I flip the color coding. Now blue is in the inside of the galaxy, and then purple, brownish colors are at the edge of the disk. And what you see is that, especially for the lower part of the disk here, there's exactly, or not exactly, but qualitatively the same spacing in birth radii. So stars at high metallicity here are predicted to come from the inside of the galaxy. And actually, that's what we see in this model as well. So this is basically explained by the fact that radial migration scrambles up a lot of the disk stars and mixes them at late time. And I hope that's enough of the motivation, because, can I go back? Yeah, enough of the motivation. So if you saw here that is oxygen over iron, what I looked at, because these old simulations, they did not have any other elements except for oxygen, which is actually a tracer of alpha elements in this old enrichment. And so my aim was to modify the cosmological code I'm using, or in general, make a framework for cosmological simulation codes to keep up with the data quality by putting in a, say, more sophisticated model for the chemical enrichment and stellar evolution. So what does that mean? Let me quickly walk you through what we do when we simulate a Milky Way in the cosmological context. So we talk about star particles, and these have like 1,000, 10,000 solar masses. So what they actually represent is a collection of stars of different masses. And so a star particle can naturally be described by a simple stellar population, where the key properties are the mass of the star particle or the population, the metallicity, and the age. I think this is fairly standard knowledge. And so in order to convert this simple stellar population into single stars, we need the IMF and we need the lifetime function. And then we can say, okay, how long do stars in a given mass bin live? And combining that with our knowledge about which stars should go supernova, which stars should result in a supernova 1A, and which go through an AGB phase, we can model the chemical enrichment in these kind of simulations. And what we need as well is a set of yields, so we know which stellar mass at which time gives us which chemical composition, so that we can feed that back to the surrounding gas. And I've implemented a way in the gasoline code to basically easily exchange the literature yields from different authors, and then run the full cosmological simulation to test the differences. And this table just shows a couple of yield sets. It's probably not an exhaustive set, and there's probably others, but these are the ones I have currently implemented and I can test. And so basically there's a given mass range given by the authors in which core collapse supernova explode. Then for supernova, there's the mass given here. And then similarly, these grids of stellar models, they have a range of metallicity in which they are calculated. But in total, there's a combination of 17 yield tables I can potentially test. Yeah. And I think I can skip over this because Chiaki did a great work of showing where things are coming from. But just to remind you, this is an average over the IMF. So basically, if you take a simple stellar population, after one Hubble time, all the stars, or not all the stars, but all the most massive stars and intermediate mass stars went through the core collapse explosions or AGB phases. And then you can calculate what's the element return of the simple stellar population after a Hubble time. And we can split that by these three sources, core collapse supernova in blue, supernova 1A in orange, and AGB stars in green. And this is for one particular yield set, which sorry, I did not put it on the slide. Ask me later if you're interested for which yield set that was. But in principle, this just shows you, for example, that magnesium is basically purely produced in core collapse supernova, while other elements have sometimes significant contributions from supernova 1A and AGB stars. And so this is important to take into account. And I think Chiaki told us how that works. But what I'd like to do here is I'd like to motivate this a little bit more, why you actually need to not only take these three sources into account, but also their time delay and their time evolution. For example, here on the x-axis, we have time again in gigayears, and then the net yield, the cumulative evolution of the net yield. Up here, this highlights which stars explode at which time. And then for oxygen, silicon, you can see again, gray gives you all the oxygen or all the silicon from the simple stellar population. And then blue, orange, and green again tell you where things are coming from. And so there's a time delay between core collapse supernova and supernova 1A. But also there's this negative net yield for oxygen, for example. And net yield just means newly produced or synthesized in the star. And what this negative yield tells you that AGB stars actually fuse oxygen and then produce more massive elements. So that's why you get a negative yield here. But then convolving that with the abundance of oxygen, which was already present in the gas from which the star was born, you again get a positive net yield, so for mass conservation reasons. And we can not only do this. Okay, yes, thanks. We can not only do this for oxygen and silicon, but other elements exemplified here. And we get similar results. You can see basically which source contributes most and when. And then this interesting bump here for carbon, where a certain mass range of AGB stars will fuse carbon, and then later on the lower mass stars, they don't fuse, because time is basically also a proxy for stellar mass. And so I think this quite nicely shows that even if you're taking the approach of a simple stellar population in the simulation, what you need to do is you need to time resolve all these enrichment and not just dump it at a certain point in time, as some people do. Okay, long story short, some results. I used the gasoline code, that's an SPH code, fairly standard physics for a cosmological simulation, gas cooling, heating, star formation from cold dense gas, feedback from core collapse supernova and supernova 1A, and elemental feedback as I described before. And in principle, I can, in a similar way as Chiaki, do all 81 elements, but I run out of memory at some point. So usually I restrict myself to 13 elements, which I trace. but rerunning the simulation with a different combination works as well. So, and in contrast to Chiaki's work, what I was interested in was merely the differences between different authors in the literature. And if I, without any fine tuning, without any matching to data, just put their yield sets in the simulation, what do I get? And one consistency check is the mass metallicity relation up here on the left for iron abundance and for total metals. Observational data in gray here from Milky Way satellites. And then blue is the old implementation from the full Nihao set, which is a set of roughly 100 cosmological galaxies. And then I picked in red a couple of galaxies spanning stellar mass from dwarf galaxies up to Andromeda type galaxies and resimulated them with the new implementation. Red is what I call fiducial, and then different combinations of yield sets are in color here, where I'm mainly focused on changing the core collapse supernova yields. And I guess what this shows is that something like total metallicity or iron abundance, they are fairly robust for Milky Way galaxies and for dwarf galaxies, and basically independent of the yield sets you choose. So that's a good thing. Total metallicity is robust. But then if we look at alpha elements, and this is the alpha element distribution for this Milky Way, which I have run with different abundances. Galar is in gray here. That's the Galar data. And then you can see in different colors, the distribution of alpha abundances. And they are quite spread out. It's not that different yield sets in the literature agree in their predictions what the alpha distribution in a Milky Way should look like. And I should mention here that this is really just due to the stellar yields, because the star formation rate and everything else is rather constant in these kind of simulations. And then probably a more familiar plot before I come to my conclusions. This is how the alpha over Fe versus FEH plane looks like in these different implementations. The upper row shows variations of the IMF, for example. I made the high mass slope a little bit steeper. I varied the delay time of supernova 1A, and I varied the normalization of supernova 1A. And as is expected, if you have less number of more massive stars, you don't produce that much alpha elements. The delay time seems to have not too much of an influence, but the normalization will shift everything to larger metallicities. And then varying the core collapse supernova rates, you can see, I guess, drastic differences from the fiducial model, for example, to this combination here, where you have way more alpha elements. And I can do this also for other elements like oxygen, carbon, and so on. But I think for the purpose of time and conciseness, let's skip that. And oh yeah, maybe some words on this. For example, oxygen, carbon, manganese, and calcium. They also show some, like carbon is quite constant for different things like the variations of the IMF, but then and I think this is expected that the IMF should not do much to this, I guess. Except for manganese, where we again see that if the less number of more massive stars actually does not bring you up to where you should be in a Milky Way galaxy. And with this, I come to my conclusion. I presented a flexible chemical enrichment implementation for, say, general cosmological simulations. You can adapt that to other codes, but I implemented that in gasoline. And I think this is great potential for Milky Way chemo-dynamics because of two things. The feedback recipes right now give you realistic galaxies with all the key properties we observe in a Milky Way galaxy. But now we need the chemistry to actually keep up with the great data coming in. And my work shows that there's a great diversity in the abundance tracks, which I had to skip over a little bit. But the data is publicly available. And once the paper is accepted, I will put the simulation snapshots here. But if you're already interested in, for example, comparing your work or using those kind of simulations, I'm happy to share the data. So just drop me a mail. And with that, thanks for your attention. And I'm happy to take questions.
All right, thank you so much, Tobias. This is really, really exciting stuff. As always, if you have a question, go ahead and do the raise hand thing, and I will see it, and I will point you out and have you ask a question. But if you guys are going to let me ask a question, this is very exciting. So there's been some really interesting work lately about, oh, Corinne has a question. I'll let Corinne go. Go ahead.
Thank you, Sarah. Thanks for this very nice talk. You mentioned nitrogen. So so I was wondering if you could comment a little bit more on nitrogen, and especially the value at very low metallicity. And I was wondering actually if some of the yields you use, there is the rotation taken into account in the models?
Nitrogen. Which slide are you referring? Like this one?
Well, this one, for example, yes, and also your plot where you were showing as a function of F average, or it's very a general question about nitrogen.
I guess
I think it was in one of your earlier slides, maybe. Or okay.
Here nitrogen. I guess you mean taking into account rotation in the stellar models?
Yes, sure.
Or,
Yeah, sure.
I guess so. Basically, I did not do anything to the stellar models. So whatever is in the grids calculated by people in literature, that's what I use. And I think
no, that I understand. Yes.
Yeah. So I did not do anything because really this my focus was on I need to take stellar yields for the stellar population I'm using, and so I rely on people calculating stellar evolution models in detail and what they put out, and so I did not do modify this in any way.
Okay, so I will have a look at Limongi and Kefit, maybe the one with rotation. Okay, I'll check. Thank you.